So yeah, I mean, so I was present perhaps in several of the early meetings, but the first, and it was a lot of fun. I really enjoyed each one of them. And in the last years, I moved more into software engineering. And this talk is going to be essentially on how relational methods can influence software engineering. I will start with a short anecdote. Like, this was perhaps in 2000 or 2001. I was attending an IFIP working group meeting, and I was giving a talk on fork algebras and how fork algebras could be used for program derivation. And this researcher, Pamela Say from AT&T Research and now at Cornell, approached me and asked me, are you aware of the alloy modeling language? And my answer was, well, no, of course not. That's nothing I ever heard of. And she said, well, you should probably take a look into it because it's a formalism that is gaining a lot of attention in the software engineering community, and it has a relational semantics and a relational flavor to it. So after a few months, somehow I remember this conversation with Pamela, and I went into looking into alloy, and I started reading the papers and understanding what the problems with alloy were, and I realized that I knew all the answers. Essentially, what I understood was that these people coming from software engineering had excellent ideas, but they kind of lacked the technical background to carry on, to actually solve the problems they were proposing. So that was a lot of fun, and I started working on how to apply relational methods, let's say, like giving a complete calculus for this alloy modeling language and things like that, and that was a lot of fun and really had a significant impact in that community. And then I realized that there were things that could be done in software engineering using relational methods that, well, people coming from software engineering alone probably were not really ready to do. And this talk has quite a lot to do with that. So let me tell you first what I'm going to talk about in this presentation, if I manage. Yeah, okay. So as the title says, this talk is on how to use some relational bounds, relational tight field bounds are they called, in order to distribute program analysis. So I will start talking about what program analysis I'm talking about, okay? Then I will move into talking about what are tight field bounds and how to compute these bounds. Then I will tell you how to distribute this program analysis using these bounds. And then I will show some experimental data that hopefully looks interesting, and then I will conclude, okay? And of course, if you want to ask questions, just interrupt me. That's a lot of fun. Okay? So the two program analyses I will be talking about are SAT-based bounded bug finding and symbolic execution. Okay. So let me tell you what SAT-based bounded bug finding is. The idea is that you have code, in this case, Java code, annotated with some contract. This contract is the green code that you can see above the Java code. And it's written in a language called JML, for Java Modeling Language. And essentially what this contract is saying is that, well, if you have a method that should find an element in an AVL tree, then the result is going to be the element, if the element is actually present in the tree, and it will return -1 in case the element is not present. And it doesn't have any requirements. The method should be able to be run under any state. And if there is any exception, then you want to realize that there was such an exception. Okay, you don't want to allow for your code to throw uncaught exception, let's say. So the code that we are going to analyze, we have a contract with precondition and a postcondition. We have a representation invariants, for instance, describing what an AVL tree actually is. And what we want to do is to detect if the code automatically detect if the code has any bugs. And for a bug, I mean if there is any input state such that executing this program on this initial state would violate the contract. Either it will reach a state that doesn't satisfy the postcondition, or it will, starting from a state that satisfies the representation invariant, will reach a final state that violates the representation invariant. And of course, the idea is that we want to automatically generate an input exposing this failure. So we developed this tool called Taco for translation of annotated code, and for tacos, because tacos are fun and are nice to eat. And what this tool does is it translates both formulas coming from preconditions, postconditions, representation invariants, and code into a propositional formula. And once you have this propositional formula, for each one of the pieces, you conjoin them. And then if you build the conjunction of the precondition, the formula that captures the transition relation for the program, and the negation of the postcondition, and that formula can be satisfied using a SAT solver, then you know that there should be an input that actually satisfies the precondition, it's a valid execution of the program, and reaches a final state that doesn't satisfy the postcondition. And that's essentially a bug, okay? So I will not get into the details of how this translation is made. That can be read in the paper. That's not so much fun, but I will show you a demo, an actual demo of Taco running, which of course, you know, this may fail for so many reasons, but let me try. So Taco, I run it from inside Eclipse just because. So let me show you what I have here. I have a code for 3 sets. 3 sets are implementation of sets using red-black trees. I will not get into the details of what a red-black tree, but essentially you can think of it as a binary search tree, a binary tree where the elements are ordered, with some extra constraints that guarantee that the tree is balanced, okay? And we have a precondition and a postcondition. The precondition is that you can always check if an element, if a tree contains a given input value. And the result that the postcondition says that the result should be true if and only if there is a node inside the tree in which the value stored equals the value that is given passed as an input parameter. What else? It says that, okay, and of course, every element that was in the tree should remain in the tree. That's an important thing. And also, yeah, okay. So that's the contract. This is the code. It's a very simple piece of code. We are just traversing an ordered binary tree, looking for the element we are trying to find. And what I will do is run the analysis from this driver that actually allows me to execute the analysis. Okay. And it says that it couldn't find any failures in this piece of code because, well, it just happens to be correct. That's fine. It's a very simple piece of code. But let's see what happens if we intentionally introduce any bugs into this code. For instance, what if instead of traversing the tree from the root, we traverse the tree from the right node, from the node that it's right hand side from the root? Something smells fishy in this case because at least two things might happen. One is that if the tree is empty, then this might throw a null pointer exception because we are trying to dereference a null object. The other thing is that we are missing part of the tree. I mean, we are starting the search from the subtree that is to the right of the root, and therefore, if the element that we are looking for is on the left of the tree, it will not be searched for. So there are some things that should make this code fail, and I will check if, let's see if something comes up when running the tool. Okay, it says that a failure has been detected, and if a failure has been detected, then the input that exposes this failure is somehow or somewhere stored in here. This is preset. Okay, let me refresh here. And in effect, it says that, well, if you use this tree, and here is a description of the red-black tree that should be used, then the method will not work. So notice that the root of the tree is a node, is not null, so this is the case in which we are looking for a value. The value we are looking for is 7, okay? And the value 7 is actually stored in some node in the tree, actually in the node 1, okay? And if we look where this node is located in the tree, let's say root is the node 1, but the node 1 is never being explored because we are starting from the right of node 1. So the root is actually being skipped. And what this is showing is that we are in a state where we are not finding the outcome will be false, that the element is not in the tree, but the element is actually stored in the tree. And this is how this works. It's fully automatic. You just have to push a button and it looks for false. Of course, you have to say something. This is bounded verification in the sense that you have to provide some bounds. For instance, in this case, we are executing loops up to 5 times, and we are considering up to 10 elements, 10 nodes in the tree, okay? Again, for many bugs, this is quite a lot. There may be bugs that will not be exposed because of these bounds. Of course, there might be, okay? So the analysis is not complete. It's complete within the bounds. Let me tell you now about symbolic execution. I mean, bug finding is like more natural. Symbolic execution, if you know it, it's great. If you don't, I will be introducing symbolic execution. And it's a technique that dates to the 70s. And incredibly enough, it was already devised in 75 for automatic test input generation. 75 automated test input generation, and the technique is, I think it's a beautiful technique. So let me tell you about it. So it works for automated test input generation, also detects bugs. If I mean, the language I am going to show does not allow you to write contracts as we did before, but you can introduce assertions in the code, and if an assertion is violated, and of course with assertion you can encode your properties that you want your program to satisfy, then if an assertion is violated, the symbolic execution engine will detect that, It's quite scalable because, I mean, something that I didn't say is that in the previous technique, the whole program gets translated as a whole into a propositional formula. So, of course, the scalability is limited to the size of the programs being translated. Symbolic execution is more scalable because things happen one path in the code at a time. Okay? And as I want to emphasize that it's quite scalable for domains, I mean, for code dealing with primitive data types, but not so much when complex objects like data structures are being handled. So we are working essentially on this problem, the problem of how to make symbolic execution more scalable when we are dealing with dynamically allocated data structures. So let me tell you what symbolic execution is. We have, this is a method that finds the minimum among 3 integer values. And what it does is, what symbolic execution does is, rather than having concrete values as we do in concrete execution, where we assign values to the variables and execute the code, it keeps symbolic values for each one of these. So I0 is a symbolic value for variable I, J0 is a symbolic value for variable J, K0 for K. And what the technique does, it executes one path at a time, okay? And I will only show you what happens in the execution of one path, but you have to bear in mind that this analysis, to be completed, requires doing symbolic execution of each one of the paths. So of course, if your code has a lot of paths, because it has while loops and nested while loops and things like that, then of course, symbolic execution suffers from path explosion, okay? And that's life. We have to live with that. So what symbolic execution does is we start from a description of the state and a formula that is called a path condition. And the path condition essentially keeps track of whatever it needs to be known about the path that is being executed. So for instance, if we execute the first sentence where the variable output gets assigned 0, then of course the state gets increased with the fact that variable output has value 0. And that's a concrete value because we assign the concrete value, and that's perfectly fine. Now, the path I chose to execute this time is one where we do not enter into the first if condition. Okay, the first if condition is not being it's not being executed. So the path condition will become the negation of the condition that was in the if. Okay, actually it's the conjunction of true and this, and therefore we keep. And now we have another condition, and in this case, we decide that we want to execute the if branch. So the path condition becomes the conjunction between the negation of the first condition and the second condition. Not the negation, but the actual second condition. Now, at this point, if I execute again, output gets the value that is stored in variable k, which has the symbolic value k0, and that's the value that output gets assigned to. Now, how do we do if we want to generate an input that traverses this path? Well, it's quite simple. We have the path condition. We feed the path condition to some automatic theorem prover. It may be a SAT solver or an SMT solver, and then it will produce as a result values for the variables, and those values are the ones that describe the input that will allow you to traverse exactly that path. So if we do this one path at a time, then we can generate inputs that traverse each one of the paths in this process. And that's how symbolic execution works in the case of primitive data types. Now, if you're trying to work with complex objects, things do not work, essentially because of aliasing among the objects, okay? So something else had to be thought of, and Khurshid, Passariano, and Visser came up with this, I think, beautiful idea of lazy initialization. And the idea is that things are kept symbolic, or attributes from an object are kept symbolic as long as they are not being accessed. If they are accessed, then you have to decide what to do with that attribute. And I will show you what the technique proposes. So let me show you with an example how lazy initialization works. In this case, I have a piece of code where, given a singly linked list, and a cyclic singly linked list, the method sorts the first two nodes, exchanges them if they are not sorted by the element that they are storing, okay? So initially we have a node whose next attribute is symbolic, and we start executing in this state. So you see, the memory heap is represented as a graph where some parts are concrete and seriously concrete node, and some parts are represented by these clouds, which are symbols, that are symbolic. They do not have a value. So the first thing we check is if next is not null. Now, of course, we are accessing now at this point the attribute next from node n0, okay? And therefore, we have to decide something. And what lazy initialization proposes is to consider three cases. Either n0.next is null, or the attribute next refers to some node that already existed in the heap, or it refers to some new node whose attributes are symbolic, okay? And this is a description of the initial state that, and now at this point, we have three different initial states that we have to consider. And of course, as in the case of the symbolic execution in the concrete case, we keep the path condition, which in this case is n0.next is not null. Now, if we look at the first state, this is a fully concrete state, so we can proceed executing the method fully concretely, okay? And if we want to generate an input that traverses the path, it's just enough to look for a solution for the condition n0.next is not null. On the other hand, if we look at the second initial state, that's forbidden because it's not acyclic, which is a requirement for the method. So that state will be thrown off because it's considered unfeasible because of the precondition. And then we have the third state, which again is the one we will consider now. And we continue the execution from this case, and now we reach the condition where we compare the values in the elements, and then we enrich the path condition, okay? But we haven't explored anything new. this is the state now. We introduce a new node T that refers to n0.next, but that's fine. Nothing new is being accessed, so nothing is being concretized. And at this point, when we access T.next, then something has to be done, and we do essentially the same thing. We have now more cases. We have one case where n1.next refers to null. This is the first case, the one in the leftmost side of the screen. Then we have two other cases where we have references to elements that were previously in the heap. And then we have the other new case where we have a new node being considered. Now, the situation in this case is that rather, besides path explosion, which still is here, nothing has changed about that, we also have an explosion in the number of states that are going to be considered, okay? So keep this in mind, because this is the problem we are trying to solve with these tight field bounds that I will describe now. Yeah, this is not so interesting. So let me show you a short demo of Symbolic Pathfinder. This is not our tool, but let me show you a demo. I need to switch workspaces. Come on. Okay. So in this case, I have an ABL tree, code for ABL trees. I have a main method here that I'm going to symbolically execute. And what this method is doing is checking, essentially symbolically executing this method repo concrete, which is a code. It's actual Java code for checking if an ABL tree is actually an ABL tree. It's over here. Actually, let me do this too. Okay, something is not working. This may happen. Okay, anyway, let me skip this because it's not that important and I'm behind schedule. So let me go back here. So what I was going to show you is that if you run Symbolic Pathfinder, then you can detect things, which of course, that's what it does. So that's not essential. But what I want to do is, yeah, definitely get into tight field bounds. So the idea of a tight field bound is that propositional variables encode the relationship between objects in the memory heap. So for each triple of two objects and a field, where O1 and O2 are objects and F is a field, a propositional variable V of O1 FO2 is true if and only if in that memory heap O1.F refers to O2. Okay, and this is the basic idea between for tight field bound. So if we use a scope of 3 nodes, we only consider up to 3 nodes, N0, N1, and N2. In a data structure with a single field, we will have 9 propositional variables that will be used to model the fact whether two objects are connected by a field on. Actually, when the solver, the SAT solver used, for instance, when doing bug finding, tries to find for a contract violation, what it does is explore different memory heaps, and in doing so, it uses these propositional variables to model the heap. Okay. Now, let's suppose that we ask the nodes in a list, for instance, to be assigned in a given order. For instance, N0, N1, and N2. Is this important? Well, in the case of Java code, it's irrelevant because object identifiers are not accessible from the code. Okay, there is no pointer arithmetic in Java. So the object identifiers assigned to actual objects are irrelevant. So we can definitely assume that objects are identified in a particular order, and that will not prevent any memory heap from being considered. Now, if we force this ordering, then, and if we have a list that is acyclic, then we know that N0 cannot point to N0. So that propositional variable cannot be, I mean, it should always be false. The same happens with N1 referring to N1 and N2 referring to N2. And also, because we are asking the order to be N0, N1, and 2, N0 cannot point to N2, okay, because first there should be N1 in the middle. N1 cannot point to N0 because N0 is before in the order than N2, and we continue in this way, and we actually are left with only 3 feasible variables. All the other ones actually can be, actually we're left with only 2 variables. All the other ones can be assigned the value false. Why is this important? This is important because the SAT solver will have to look for evaluation, and the complexity of the SAT problem is NP complete. And the worst case, of course, is exponential, and therefore, at least of all the known algorithms that we know, and therefore, if we have fewer variables, we get an exponential speed up. Okay? And in doing so, we use what are called symmetry breaking predicates. And symmetry breaking predicates essentially do this. They impose an order between the nodes so that we can get rid of more propositional variables because of this symmetry breaking predicate. Now, let me define properly what a tight field bound is, given object identifiers N0 through Ni and the field F. The tight field bound associated with F is a minimal binary relation on N0 and 1 unknown, such that Ny and J, the pair N1 and J, is in the field if and only if there exists a valid memory heap satisfying the symmetry breaking predicates in which Ni.F equals Nj and or null. So let me remark 2 things. First, valid. By valid, we mean that the representation invariants, whatever they are satisfied. So if we are working with ABL trees, then the ABL tree is there. And if we're working with red-black trees, we're talking about red-black trees. And the symmetry breaking predicates force nodes to be assigned in a certain order, and then we can efficiently, we can do 2 things. We can compute the tight field bounds, and we can get rid of much more propositional variables. And getting rid of propositional variables, it's very good. So essentially, the order that we are imposing on the node identifiers or the object identifiers in the heap is a BFS traversal. So essentially, the symmetry breaking predicates are kind of rules that force some ordering to be guaranteed. So the node in the row is always n0. Then the ones that are under some element have bigger numbers and unsorted from left to right according to the order in which the fields were declared. And this is how it works. Now you may wonder why to the left of n0 we have n1 and not n2. Well, that's because another rule that is not appearing here is that there cannot be holes. And if we only have 5 nodes and there are no holes, then things have to be compressed to the top, and there cannot be a hole where from n0 to n2 to the left. So there are 2 algorithms for computing these tight field bounds. I will only discuss the sequential one. And the idea is that the sequential algorithm incrementally asks the SAT solver for valid heaps, with the constraint that each one of these heaps has to contribute at least 1 new pair to the bound. Okay? Eventually, the SAT solver will say, okay, and SAT, I cannot contribute anything else, and then the computation of the tight field, of the upper tight field bound, that's how they are called, is completed. And whatever pairs are not in the bound, we know that we can remove the propositional variables that are associated to those pairs. For instance, if we have ABL trees with up to 4 nodes and fields left and right, and I will only compute the bound for field left on the top right, then we ask the solver for a ABL tree, and it gives us this tree here. Then we know that this pair has to be in the bound. Then we ask another tree, and it gives us this one. This one doesn't contribute anything new to the left field. This one contributes a new pair, the one from n1 to n3. So the new bound is the one where we have 2 pairs. The next one doesn't contribute anything new to left. The next one doesn't contribute anything new to left. And this one contributes 1 new pair. And essentially, if we have ABL trees with up to 4 nodes, that's the tight field bound for the left field. Now, if we have 4 nodes, the number of variables that we would use to model this field, the left field, would be 20 variables. Out of these 20 variables, we're actually keeping 6. These 3 plus the 3 where n0, n1, and n2 can point to null. Okay? So 6 out of 20, that's a pretty good decreasing in the size, and it will show a significant impact in analysis. Okay? Now, okay, similarly, you remember how lazy initialization works. You have this, the significant part of lazy initialization that can be affected by the presence of tight field bounds is that part where we are accessing a new node and deciding what the possibilities are. In this case, the idea is that whenever we analyze the possibilities, we constrain to the possibilities that fall within the bounds. The ones that are not in the bounds are not ever considered, because essentially those are possibilities that will never lead you to a valid input for the program. Okay? And in this way, there are fewer cases to consider, and the exponential explosion that suffers from lazy initialization gets reduced in this way. So if we look at the case for symbolic execution, we know, and we have the the partially symbolic heap on the top, and we access the field that has the cloud, then we get 4 possibilities. Out of these 2 possibilities, we know that 2 can be removed because they have cycles, and we don't want cycles in these, let's say, trees. These are the left field from a tree, so trees do not have cycles. We can remove those 2 straightforwardly. Now, if we look at the one that survives to the right, the one that has 3 nodes and then points to the left to a symbolic node, then we have all these possibilities. Now, keep in mind, we are talking about structures with up to 4 nodes. Now, these 3 we can remove because they have loops, okay? But what about the 4th, the one that is to the right? Is that valid or not? Well, actually, it cannot be, because if we try to assign identifiers to the nodes, I mean, the number of nodes is fine. It has 4 nodes, and we are considering 4 nodes, okay? But there is no way that this can be part of a AVL tree, of a valid AVL tree. And the reason why, how do we know that? Well, because let's see what the bound says. The node in the top, we can call that N0, and to the left, it can only have null or N1. Since it's not null, it has to be N1. Now, N1 can only refer to N3, but N3, if we go to the left, can only refer to null, not to a node. And that means that there is no valid AVL tree or red-black tree where that configuration can occur within a scope of 4 nodes. And then we can remove also that, that input from the possibilities for lazy initialization. So let me get then to the main part of the talk, where we actually discuss how do we profit from these tight field bounds for distributing the analysis. And the idea is very simple once you know it. So here we have fields left and right for red-black trees with up to 4 nodes, up to 5 nodes, sorry. Okay, so this is a binary relation between nodes. Pairs of nodes or null are contained into the upper bound for left or right. And whatever is not here essentially is non-existent. Now, fields or attributes are functions, okay? Therefore, if we look at these bounds, we have a degree of non-determinism that it would be nice to remove from this bound, okay? Why it would be nice? Because if we can remove more pairs from the bound, we know that the analysis gets improved. So ideally, what one wants is to have a tight field bounds that are functions. But of course, that's not the reality. I mean, that depends on what the data structure is. Now, these are the fields for red-black trees. The bounds for fields left and right for red-black trees. But what the idea for distribution is the following. Reduce the non-determinism, okay? Rather than having these bounds, consider more bounds, okay? So let's look at field left. We have 2 possibilities for node N0. N0 can point to N1 or N0 can point to null. Similarly, for node N1, N1 can refer to N3 or to null. And in any valid actual memory heap, only one of those possibilities is valid. So we can actually split this bound into 4 bounds. One where N0 points to N1 and N1 points to N3, another where N0 points to null and N1 points to N3, and the other 2 possibilities, and then we get 4 possibilities. And now we have 4 problems. Each one is a valid upper bound for a red-black tree. And if we split in this way, we are considering all the possible configurations. So we are not missing configurations because of the splitting. Now, of course, if we do that only for left or for field left, we get 4 sub-problems. If we do it for 5 fields left and right, and for nodes N and N0 and N1, then we get 36 sub-problems. And 36 is a number that it's quite small. We can use any distributed system for analyzing 36 of problems. That's not a problem. Now, what if instead of considering only N0 and 1, we do it with more nodes? Well, this explodes, okay? So if we want to remove the non-determinism from red black trees with up to 15 nodes, which is the number of nodes that one usually uses in analysis, and we want to reduce the non-determinism or remove the non-determinism for the first 6 nodes, then we get 33 million problems. And that's not so nice, okay? That's actually, that's not nice. So we came up with some ideas in order to tame this problem explosion, and actually the combination of these works extremely well. One is, do not ever consider those problems that violate the symmetry breaking axiom, okay? So when you remove the non-determinism from some of the nodes, a part of the memory heap is fixed. There is no non-determinism. It is a fixed, let's say, prefix of the memory heap. And then you look at that part, the part where there is no non-determinism, and you check if the symmetry breaking axioms are satisfied. If they are not, get rid of that. That is not important. There is other problem that will satisfy the symmetry breaking axioms and models the same. The other thing is to mine aliasing information. So if we are considering data structure where aliasing is not an option, like for instance, in the case of trees, then if the subproblem that you are obtaining from removing the non-determinism has aliasing, then just get rid of that too. And the other one is to check that the class invariant is satisfied. Now, essentially, when you remove the non-determinism together with the symmetry breaking axioms and everything, it might be very well the case that you have a fixed part of your problem that can never be part of a valid structure. For instance, if N0 goes to through left to null, let's say there is nothing to the left of the root, and then you have at least 3 elements to the right in the memory heap that you are considering, then that cannot be a balanced tree, okay? And if we conjoin these 3 properties, then we get a huge reduction in the number of problems, like the optimization 3, for instance, for the case we were discussing just before, allows you to move from 33 million problems to actually 172, which is quite striking. I mean, that's another, it's a completely different problem. Now, it is completely doable, okay? And the same for the other data structures that I'm showing here. So, sorry about this. I have to do this now, or I will not be able to sleep tonight. Okay. So these are some experimental results that we obtained from, I just copied from the paper. What are these showing? They're showing for 2 data structures, 3 sets and binomial heaps, how the analysis is improved from the sequential case where we use tight field bounds. We are using tight field bounds in the sequential case. How does it improve whenever we use the distributed case? Okay, what is the speed up that we get using this is running on 64 computers. It's a cluster of 64 computers. It's not a 64-core computer or anything like that. It's actually 64 machines in a cluster. It actually is a student's lab at the university. Okay, so if we look at, let's say, a case that is more interesting, the insert case in 3 sets, that's the analysis of the method insert for inserting a new element in a 3 set. If we use the non-distributed version, it essentially times out, and timeout in this case is 10 hours timeout, okay, for scopes 10 and over. while we get very decent times using the distributed version. The speed ups, if you look at the notation for the speed ups, well, you see a collection of greater than symbols, and that means, well, the first means that the speed up is greater than 69 because, well, the first analysis timed out, so we do not know what actually took, but we know that the speed up has to be greater than 69. Now, when we move to scope 12, since the timeout is 10 hours, you might say, well, this is 10 point something speed up, but that's not fair because we know that these analysis times grow exponentially. So there is no way that this is going to take just a bit over 10 hours. This is going to take way more than that. And what we do is we add a new greater than for each scope that we are able to analyze that was not analyzable before. So the speed up for scope 15 is not 2.5, it's probably close to infinite, let's say. It would never finish in the non-distributed case. And the same for binomial speeds, okay? So in the case of symbolic execution, we have run part of the experiment. We haven't finished with this, but these are some of the interesting cases. This is symbolic execution of a depth first search traversal of an AVL tree. And again, we are presenting this in a log scale graph. And well, you can see, I mean, this means that the speed up is very, very important. I mean, the distributed case is a smooth line, while the non-distributed case has a very much steeper slope. So that's significantly worse. Same in here, in some cases, for instance, for AVL tree insert, the non-distributed version runs out of memory, while the distributed one, because we are considering much smaller problems where the number of inputs that have to be considered is much smaller because the fields, the bounds are much more refined, then we can deal with the amount of memory that is required for running the symbolic execution engine. And just to conclude, okay, here's another example. Here is a video. I cannot run it from here because of many things, but the pandemic is not helping. But I can show you how this works. So this is a distributed symbolic pathfinder. And what this is doing, let me eventually post it if I can. No, I can't post it with that. Well, okay, posting it is not going to be easy. Okay, so what I want to call your attention is to a column where it says, what is the reason for a problem being solved? And the possibilities are not error found because of the invariant. You see that many of the cases actually die because of that. This is one of the optimizations that allows you to get rid of problems. Another one said SPF, which means that the analysis completed or not, but it was a decision of SPF. And the way it works is that we have queues where problems are assigned, allotted some analysis time, and if they time out, okay, this is a very interesting thing. You remember that we cannot remove the non-determinism from all the nodes because the problem explosion would be too high. So what we do is we remove the non-determinism from some of the nodes, okay? And in order to get enough subproblems to populate a queue that has a maximum size. Now, when a problem is removed from the queue and sent to a computer, the idea is that that problem has some time to execute. Now, if that time is elapsed, then that subproblem will be enqueued for being refined, okay? So it's bound that is partially refined will be refined even further. And the idea is that that problem that was difficult at that time and reached the timeout because it was being refined, the subproblems that spun from that problem will be more efficient and hopefully will be analyzable within the elapsed time that they were assigned.
Marcelo, I'm sorry, I think you need to come to an end.
And I have. So the conclusion is that whenever you have an analysis technique in which you can introduce somehow tight field bounds, you have available a method for distributing your analysis for free, okay? So one interesting thing to do is, okay, what kind of analysis am I doing? Can I use tight field bounds in this context? Will it help? Well, then if it helps, then it will help much better if you distribute the analysis. And that's it. Thank you very much.
Thank you very much, Marcelo, for this very interesting talks. Now we know what you've been doing all these years, unless we have read your papers anyway. But I think we still have time for one or two quick questions. So who would like to ask a question, please? Yeah.
Hello. So first, thanks for the talk. So my question is, with these tight field bounds, it seems to me that the problem you want to solve is also caused by the fact that you get lots of isomorphic graphs. If you consider this as graphs, if you get several graphs that are actually isomorphic to each other and you want to stop exploring a path where you have already found a graph that is isomorphic, is there maybe another way to do this? I mean, kind of to check for isomorphic graphs? Or I mean, let's say I'm trying to view this in a context where maybe instead of the more propositional view, you look at this more in terms of graphs and graph isomorphism.
Sure. Okay. Yeah. Thanks for the question. So one thing, there are no isomorphic memory heaps. I mean, there are no isomorphic graphs in these techniques. Both lazy initialization and backfinding using symmetry breaking are guaranteed not to ever consider isomorphic graph, okay? So that's an important thing. So what I would say is the main problem we want to solve is not, I mean, that was a problem, an important problem, but the people who proposed lazy initialization took care of it in the case of symbolic execution, and we did our share of work in the case of backfinding by introducing the symmetry breaking predicate. Now, the problem we are trying to solve is to remove or to reduce the number of memory heaps that are describing invalid structures, okay? I mean, structures that, I mean, we are only consider one for each isomorphism class, but there are many isomorphism classes where the structures that we have, for instance, they have loops, the graph have loops, the graphs have a disbalance in the case of balanced trees that cannot be ever made into an actual valid balance structure and things like that. That is the kind of constraints that we're trying to capture with this abstraction of tight field bound.
Thank you. Another question? Yes, okay, we have someone.
I don't know whether you are aware about, there is a paper by, I think, Karbyshev and other people from the Journal of the ACM, and also previous paper on CAV, and they used and they adapted the IC3 algorithm to the EPR fragment, and they made experiments from distributed algorithms and also from linked lists and heap memory and so on. Are you aware about that? And can you compare with that?
Can you repeat the last name of the author, please?
Can you compare with such an approach? Or
No, not the question. Just the name of the author, because I want to understand who are we talking about.
There is a paper by, I think, Karbyshev, Björner, and other people in the Journal of the ACM.
Okay, yeah, okay, Nikolai Björner, yeah, sure, okay.
The title is proving universal property or showing that their absence or something like that. I mean.
Yeah. Okay. Let me try. Okay, we haven't compared with that. When is that paper from? Do you have it? Is it a new paper? Is it an old paper?
There is a conference version at CAV some years ago, and also in the Journal of the ACM.
Yeah, okay. I will look into it. I am aware of part of their work, in the sense that, for instance, work done on Daphne and things like that at Microsoft Research at the time. And we compare with some of the tools they have, like PEX or some other tools there. And for data structures, TACO was much more efficient. Now, I'm not sure I'm being fair, because I'm not saying I'm comparing with exactly that work. So I don't want to give that impression. I haven't compared with that work, and I'm making a note right now. But thank you very much. Yeah.
Okay, thank you very much again, Marcelo, and thank you for all the questions.